Hi, this is Peter Weiss, and this is my final microprocessor circuit. In this video, I'm going to be just showing all the different parts of the circuit, how they fit together, and then I'm going to do some tests just to show that all of the parts and components work as they should. So, there are a lot of parts to this microprocessor. This is my FSM. Basically this whole thing here. This is essentially two registers storing the values for S1 and S0, the current values, and then these two gates are the next state logic. And what this does is it just loops back and forth between 0, 0, 0, 1, 1, 0, 1, 1, which are the different states of the microprocessor, because we don't really care. It's a very simple FSM because the next state is only dependent on the current state. We just have two fetch states and two execute states every single time, no matter what. And then directly connected to the FSM is the output decoder, which creates all the control signals for the microprocessor. So the output decoder is dependent on S1 and S0, the current states, and then 4 bits of instructions, which are taken from the instruction register, which I'll talk about in a second. So we have 4 bits of instructions and 2 bits for the state, and then we just do a bunch of logic just to get these control signals. And what these control signals control are enables for tri-state buffers. So that's what all of these are. They're enables for tri-state buffers here, 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 and here. Enables, which are like loads for registers. Those are these EN signals, and I use tunnels for these just to make it neater. But these signals go to the load inputs of the registers, so here, here, and here. And they enable these registers to read from the bus the whatever data is currently on the bus. These tri-state buffer enables enable the registers to output to the bus, to write to the bus. And then this last control signal here is the add and not subtract signal that goes directly to the ALU that determines whether we're adding or subtracting only when the ALU is being used, only when we're adding and subtracting. And then I have 2 other control signals here actually, which are separate from this because they're not dependent on the instructions, only on the states. So this one, this one loads the instructions from memory. It goes to this load enable of the instruction register, so it enables these instructions to read the data that's currently being fed to it from memory. So it loads the next instructions, and this one increments the program counter so we can have different instructions in the program. And if we can look at these in more depth, these circuits. So the FSM again is these are just 2D registers with the next state and the current state, and just a clock and reset. And again, the next state logic is here, so the whole FSM is this, not just this block. And the output decoder is just a lot of logic just to get these different signals, which I talk about in my report, and I'm not going to go over here because it's too much, but it's just combinational logic, similar to these. Then I have, so that's the FSM output decoder. This is the program counter and the memory for the microprocessor. The program counter is basically just a counter that counts based on the clock when increment is high, so only when increment is high will it count up by 1. So that's why this signal is sent to increment the program counter. And the program counter is just a 4-bit counter, which I designed from these full adders and registers, which I again talk about that in another video, but it's basically just a 4-bit counter. And then the memory stores the data. This is perhaps like the most important part, and this is what I'll be editing in this video to test the microprocessor. So this just stores the data and the instructions that are going to be executed. So these are all the instructions, 16 total instructions, 8 bits wide, 4 bits for the instructions, 4 bits for data, and it's controlled with the pointer that comes directly from the program counter. Yeah, so that's the program counter in memory that steps through the program and stores the data for what the program actually does. This is the instruction register, so the outputs from data get split into the 4 bits for the instructions and the 4 bits for the data, which each get stored in these 4-bit register files. These instructions go directly to the instructions for the output decoder to get the control signals, and the data goes to the bus dependent on this tri-state buffer here, which enables the data to go there whenever this output goes high. And then I just have all the other registers here. So this is A register, which can read from and write to the bus. A B register, which can just read from the bus, controlled with this signal, the ENB. The input register, which can write to the bus when this is high. The output register, which can, again, just read from the bus when this ENO is high. And the input is controlled by the user. The output is displayed on this this hex digit display right here. And I also code these probes so you can see the output for A and B. And the ALU either adds or subtracts B depending on what we want to do. And these are all either connected to the bus with the tri-state buffer or depending on this load input here. And this is the bus. So this is a 4-bit bus. There are 4 bits for all the data connected to this bus here. I just used one wire because it was neater. And the only other parts of my circuit are the clock, which everything runs on, all the registers, and the program counter. All these 4-bit registers on the program counter, including the FSM, which uses registers, runs on the clock, so we need that. And we need the reset just so we can start the simulation to give all of these registers an initial value. So if I enable this simulation, if I reset it, it'll give everything an initial value, and I'll be able to run a program. So currently, the program is determined entirely by what's in this memory block here. Currently in memory, I have these instructions preloaded. So these instructions are, I entered them with hexadecimal, but this is the binary representation. So 1, 3, or 0001, 0011, that's, 1 is the add instruction, and 3 is the data. So this means add 3 to whatever the current value of register A is. The current value of register A, because we reset it, is just 0. So currently we're going to add 3 to A, and then 4 is the instruction for display to output, and 0 is the data associated with that, but since we're just displaying the output, we don't need data. And I just have those repeatedly, just add 3 to A and display to output. So add 3 to whatever's in A and display that value to output. So since I currently have these instructions just repeated, it should just add 3 repeatedly to A, and once we get to 15, it'll just loop back around to 0, so it'll just keep adding 3 and displaying the output. Now we can step through this slowly to see what happens every step of the way. So currently, the state is 0, 0, so this is the first fetch state, and the only one of these control signals that is high is this load instructions signal here. So currently we're going to load the first instruction from memory. The instruction corresponding to 0000, which is the current address, the current point in the program. So that instruction, like we said, was add A. So it's going to load 0001, 0011. So 0001 is going to go into instructions, and 0001 is going to go into data. So I'm not going to be able to see that, but it loads that value into this register here when I take the clock. Now, the next thing that's high is the program counter, the increment for the program counter. So when I take the clock, the program counter is going to increase by 1, and we can see the address here goes from 0 to 1. So those are the 2 fetch states. And now if we have the execute states. So the first execute state, if we're adding, first we want to store the value that we're adding, which is in this data, which is 3 right now. We want to store this in B to begin with, because we need to add it to A. So if we store it in B, the enable for this tri-state buffer for the data is going to be high. So we're going to put this data onto the bus, and when that data, it's currently on the bus, so if we looked at this bus right now, it would currently have a value of 3 on it. And then the next clock pulse, we're going to load that into register B, because the load for B, the enable for this load for B is high. So if I take the clock, we're going to see the data go into B, so 3. The current value of 3 go into B. And now that's the execute 1 state, and now we have the execute 2 state. So the execute 2 state is when we actually add the data from A and B, and we store it into A. So if we're adding A and B, well, the ALU always adds them, but we want to make sure we're adding them and not subtracting, so this add / not subtract has to be high because we're adding. So we're adding A and B, and we're taking that value and putting it onto the bus. So this enable for the ALU for the tri-state buffer is high because we're putting the value that the ALU is adding onto the bus to for it to be available, and now we're enabling the load for A, so that data is going to be stored into A. So on the next clock pulse, we're going to see A plus B, which is 0 plus 3, stored into A. So 3 is going to get stored into A. Yep, and so that's exactly what happens. So that's the add instruction. So we added the data, which was 3, to what I was in register A, which was 0. So 0 plus 3 is 3, so now we have a 3 in A. Now the next instruction is to take this from A and put it to the output register. So you would see a 3 here. So first we do the fetch states. So we enable the data from memory to be loaded into the instruction register, so instructions know what to do. So that happens. And now we increment the program counter, so we're ready for the next instruction. So now the program counter went from 1 to 2. And now the first execute state of the display to output is we want to enable the A to write to the bus now. So now instead of ENA, which loads the data from the bus into A, we do EA, which enables the tri-state buffer to put the data from A onto the bus. And at the same time, we enable the load for the output register. So ENO is high, so the output register will read from the bus the data that's currently on there, which is 3. So now in the next clock pulse, we should see a 3 here. So now we have 3 in the output register displaying to output. And now we have execute 2, but since we already completed what we needed to do, the data already was transferred from A to output, the execute 2 doesn't do anything in this for this instruction, so nothing happens. Nothing needs to happen. And now, if we keep ticking the clock, the same thing will happen. We will add 3 to the current value in A, and then display to output. So 1, 2, now execute 1, execute 2. Now there is a 6 in A, because 3 plus 3 is 6. And now, if we step through the display to output, we should see the 6 go to output. So now the 6 is an output. And I can enable the clock, so currently I have the tick frequency of 16 Hertz, so it's fairly fast. So if I enable the clock to just tick, we see that the value in A, 3 is added to A, and it's displayed to output. So we're basically just counting by 3. So we're adding 3 every time, and of course we're in hexadecimal, so we have like A, B, C, D, E for 10 through 15. So you can see we're just adding 3 every time here. So I'm going to stop this. So that simulates the add instruction and the display to output instruction. And that's because I had those instructions in memory. So add 3, 0001, 0011 is add 3, and 0100, 0000 is display to output. But now if I change these, we can do different instructions. So why don't we try subtracting, repeatedly subtracting now. So if I change it to 25, we have 0010, that's the instruction for subtraction, and the data is 0101, which is 5. So now I can change all of these, so now this should basically count down by 5 in the same way that we were adding before. Now it's exactly the same except we're subtracting, so this signal here, add subtract, is going to be low instead of high, and we are changing the data a little bit just to test it from 3 to 5. So let's do that. And we want to display to output every time because we want to see the output, and it also shows that the output works with more than just adding, which it should. So we change these all to 25. And now we can step through it. First let's reset it just to get the value to 0. We can step through it, but so first we're loading instructions, then incrementing the program counter, and now we're enabling this data, which is 5, to go into register B. Now we are subtracting A minus B this time because add subtract is low. So we're doing A minus B and storing the value in A. So currently the value of A is 0, so 0 minus 5 is going to be negative 5, but that's equivalent to 11 mod 16. So we should see a value of 11 go into A, which we do. 1011 is 11. And now we have loading the instructions for the next instruction. So fetch 1, fetch 2, incrementing the program counter, and now displaying it to output. So enabling A to output to bus and output reading. So now we should see an 11 here, which is B in hexadecimal, which we do. And if we just let this tick repeatedly, we should see counting down by 5. So C 7 minus 5 is 2, minus 5 is D, which is 13, minus 5 is 8, minus 5 is 3. So we're just counting down by 5 every time. So now instead of repeatedly subtracting and displaying, or adding and displaying the output, we are repeatedly subtracting and displaying that value to output. And of course we can change the data, but it should work with generally any data. Now we want to test the input. The second to last thing to test is this input register here. So if we reset all of this, we've reset everything to 0. Let's change the instructions so now we can read input. So reading input, the instruction for that is 3, 0011, which is equivalent to 3. So I want to instead change these from not subtracting, so not 2, but 3. And again, the data doesn't matter with reading from input because the data comes from what's in the input register. So the data in the instruction register doesn't matter. So I'm just going to set that to 0. And we can change these all to 30 just so we repeatedly read from input. And I'm not going to let it tick very quickly this time because that'd be kind of boring because I have to physically change the input myself because it comes from the user. And I'm not as fast as a 16 hertz clock. So we're changing these constants. So now we're going to just read from input and display that to output. So let's change the value of the input to something interesting. Let's say, I don't know, 14. So now the current value of input is 14. So we do the same thing. We loaded the instructions. Now we're incrementing the program counter. Ready for the next instructions. And now the enable for the input to write to the bus is high. So now whatever's in this register, which is currently 1110, is writing to the bus. So now the data is on the bus, and we are storing it in register A temporarily. So now if next time I tick, we should see 11 go to register A. Or sorry, 14 go to register A, in which we now have 14 register A. And again, the second execute state doesn't really do anything because the data is already in A. We've already completed the instruction. And now we want to display that to output, and we will see 14, which is D, or sorry, E, yeah, 14, which is E in hexadecimal, go to output here. So now we have the 14 here. And I can change the input and load a different number, so I don't know, 7. So first this goes into register A. Now we have a 7 in A, and then it goes to output. So now we have a 7 in output. And whatever data I enter here, so now let's try 9, goes to register A, then to output. And I can try whatever data I want for it goes to A and then to output. So that's how the input register works. I have to manually control this myself, so I can't let it tick very quickly, because if I let it tick very quickly, say I change this to, I don't know, to 10, which is A, and I just let it tick, the A is going to go to output, but then it's not going to change because it just keeps reading from the input register, which is still A, and I would have to change this quickly, but I guess I can try that now. This is 8, 0, 2, 3, 7, 5, goes into A and then to output every time, so it eventually changes. And yeah, the input is loaded into A and then into output every time. So that's how the input register works. And now the last thing to test is the load accumulator, the LDA instruction, which just takes this data from memory and loads it into register A just directly. So the instruction for that is 000101, so 5, and then whatever data we want. So you can change this now. Instead of 3, we want to change it to 5, and let's load, I don't know, 2, then 6, then I don't know, B, which is 11, then 9, then E, and every time, again, we're displaying it to output so we can see it. I don't know, 1, this is just random data, it doesn't matter what it is, 4, and let's say 7. So now when we tick through this program, we're going to see the data go in A first, and then to output go from 0. Well, we start at 0, then go to 2, then 6, then B, then 9, then E, then 1, then 5, then 7. So let's reset this. And now as we tick through this, we can see the value go into A. So now we have a 2 in A, and then it goes to output. Now we have 2 in output, and if we keep ticking through this, the data from memory goes first to A. So now we have a 6, and then to output. So 6, B, 9, E, 1, 4, 7, and now we should go back to 2, which was the first number. So we ticked through the entire program, and we loaded the data that was in memory into register A, and then into the output register. So we just had 2, 6, B, 9, E, 1, 4, 7 go into register A, and then to output. So that shows, now we showed adding what's in A and B, subtracting what's in A and B, taking input from this input register here, taking input from the instruction register, loading it into A, and displaying and taking A and putting it into output. So we showed all 5 operations with different types of data, and now we can just do one last test where we do a combination of all of them. So let's say we keep this. So first we load A to 2. Now let's say instead of loading A to 6, we add 6 to A and display that to output. And now let's subtract 4. And now we can, I don't know, add 9 to that. And why don't we now just take input? So now we take from the input register, so we load 2 to A, we add 6, subtract 4, add 9, and now we're just erasing that to take data from the input register. Say we want to add 5 to that, add another 3, and then maybe subtract 7. So now we can see this program. This is just a random program, but we can see it. We can see what it does. So if we reset everything, now the first thing that we're going to do is load 2. So let's do that. We load 2 into A and display it to output. And now we're going to add a number, 6. We're going to add 6 to A. And display that to output. So now we have 2 plus 6, which is 8. And we're going to subtract a number, which was 4, I guess. So we're subtracting 4, and 8 minus 4 is 4. And now we're adding another number, which is 9. So 4 plus 9 is 13, which is D. So now we should see D, which we do. And now the next step is to take data from input. So I don't know, let's load 10, which is A, into register A, and then display it to output. So now we have A, and now the next thing is we're going to be adding something, or subtracting something, I forget. So we're adding 5 to A, so A plus 5 is 10 plus 5, which is 15, which is F. And yep, now we have F and A, and 1, 1, 1, 1, which is F, and we display that to output. Now we're going to be subtracting 3, so F minus 3 is 15 minus 3, which is 12, which is C in hexadecimal. Or sorry, we're adding 3, so F plus 3 is 15 plus 3, which is 18, which is 2 modulo 16, so now we have 2, and now I think we're going to be subtracting something. Subtracting 7, so 2 minus 7 is negative 5, which is 11 mod 16, which is B, so we should see a B. Yep, and that's the end of the instructions. Now if we keep going, we just start over by loading 2. Yep. So that's just a bunch of random instructions incorporating adding, subtracting, taking data from input, and loading data to A, and outputting it to output every time. And we can watch this program happen very quickly. So it's not that many instructions, because memory is only 16 different instructions, so it's just going to keep repeating. But yeah, this displays how my microprocessor works in as many states as I could practically. This is as many different instructions as I could practically fit in one video. And this is the last video I'm making for my microprocessor for my final project. Thank you.